All right, I'll get started.
Good.
Yeah.
All right. Yeah, thanks for having me. Yeah, I'm a little sad not to be there in person this year. I had a great time last time. So yeah, I hope you have a great couple of days and enjoy the happy hour this evening. So I'm going to talk a bit about some work I've been doing over the last year, looking at building an emulator of GFDL's CICE model. This has been a really big collaborative effort between a bunch of folks at different institutions. And a lot of this is really built on the back of the work that's been done at the Allen Institute for AI, who's really been kind of like steering the way in terms of developing code bases for climate model emulation. So a lot of those folks have been involved in this effort. Just before I start, I wanted to do a little shameless plug that we had a paper out last week. This is on some results I presented at this meeting last year, talking about some work we were doing at building a hybrid version of GFDL CICE model, which does a machine learning state-dependent bias correction. So you can check out the results of that if you're interested last year. And we've also had another paper led by Lausanne looking at kind of more broadly this framework for hybrid physics AI ocean CICE models. And in that, we showed some more results from this hybrid CICE modeling approach, looking at kind of longer integrations and showing that we can kind of reduce the biases in the GFDL coupled model with this approach. But yeah, I'm here to talk about climate emulation. So I guess just to give a brief one-slide recap, kind of hybrid modeling and numerical modeling feeds nicely into this, just in the sense that, climate model emulators are gaining a lot of traction these days, just as a way to build fast approximators of climate model components. And one kind of framework which is really pretty popular is this notion of autoregressive climate emulators. So we can think of F here being our machine learning model, which is integrating the state of the system from time t to time t plus delta t sometime in the future, and then that prediction feeds back into the model and it kind of rolls out iteratively. So one paper that we put out last year in collaboration with this Allen Institute group was looking at coupling a 3D atmosphere emulator with a 3D ocean emulator and produce this nice global coupled emulator, which in the paper we quoted that it has a really fast throughput of 1,500 simulated years per day. It's emulating the GFDL CM4 model. These aren't totally apples to apples because the CM4 has a quarter degree ocean and sea ice, whereas Samud Race is all 1 degree, but it was a nice achievement nonetheless. But looking a bit closely into some of these emulators, so this is Camulator, this is Will Chapman's work on emulating CAM. This is that Samud Race model, and then the atmosphere-only version of that, ACE2, and this is looking at the surface temperature biases in each of these respective models. And something which stood out to me a little while ago was looking at the polar regions in some of these plots, and you can see that that some of the largest biases in these models exist within the polar regions, and that got me thinking about sea ice and the way sea ice is represented within these models. And for some of these, sea ice is just given as a sea ice concentration is like a forcing term where we just give that as an input to the model. In this Samud Race versions, sea ice concentration is an input and output variable, but in all cases, sea ice has a relatively simple representation within these models. So I was kind of interested to see, this is kind of building towards the broader scope of what this work is about, is trying to see if a more sophisticated sea ice emulator can improve the representation of, or improve biases within these data-driven emulators. So I'm just going to jump in and show some results straight off the bat. So this is FlowNet. This is an emulator of the GFDL sea ice model. The top row is showing the numerical simulation. This is OM4. So this is reanalysis forced. This is the sea ice concentration, the sea ice thickness, and the snow depth. And then on the bottom is the emulator. So yeah, we've trained it on this simulation and we're rolling it out in a held out period for a year. And you can see, like, in the concentration, it's responding really well to the dynamics. You can see kind of storms evolving across the sea ice there, and it's getting the kind of nice retreat of the sea ice into the melt season. And similarly, we're losing the snow cover as well. And then as we start to come out into the growth season, it's kind of matching the numerical simulation really well, and getting the right sea ice thickness spatial pattern too. So that's a really nice kind of validation first off of just it looks like it's doing the right thing in this animation. So yeah, I just want to kind of dig into what what FlowNet is doing under the hood. So we've framed it in this mass conservation framework. So what we're doing really is we're not actually emulating the sea ice concentration and thickness themselves, but we're actually emulating the mass tendencies which make up the sea ice mass and or area evolution. So this equation on the right just showing that, for example, if this were concentration or thickness, we can think of that moving forward in time as a function of these sources and sinks and transport convergence related to each of those. So these are the names in the CIST of the CIST diagnostics, and I've just for SAIS users, I've put the kind of equivalent ones here on the right. So yeah, we're forcing this constraint for the emulator that as it integrates forward, the sea ice mass change, for example, has to either be coming from growth terms or melt terms or transport terms. And this is just highlighting that relative to the underlying simulation in orange, we're kind of matching this seasonal evolution of growth, melt, and advection in both hemispheres. And we can do the same for, this is for sea ice concentration, similar budget decomposition, and also for snow as well. I couldn't find with a quick grep what the SAIS diagnostic. Maybe someone can tell me at the end what that is. So I just wanted to show some results, and we're going to make a comparison to what I'm calling a full state model. This is basically the same architecture, but it's not enforcing this mass conservation. Instead, it's just emulating these similar sea ice mass and snow mass terms, but we're also giving it the velocities to try and help it a bit. But yeah, it's not doing mass conservation. So if we look at some validation metrics over, for example, these are this climatology sea ice thickness. These are just averaged over this validation period here. So we've got a training run from 1969 to 2005, and then we've got a 17-year validation period. So this is just comparing the mean sea ice thickness between our FlowNet and then this kind of other baseline model. You can see FlowNet's getting the kind of mean spatial pattern really well. This full state model is slightly biased in its thickness and has some grid scale noise there, but doesn't do a bad job. But yeah, so FlowNet's definitely doing better here and getting this trend over both the training period and the validation period in sea ice volume. And then, just to emphasize, this is a global model, so it's also doing really well in the Southern Ocean. Getting that variability, or it looks like as well this is the annual mean anomalies in sea ice volume. And then snow depth, again, we're capturing the spatial pattern of mean snow depth pretty well. And then something going on with this, the full state model in terms of its grid scale noise. Some other studies have noticed this in like the ocean. They've seen that sometimes you get imprinting of the fast evolving velocities on the slower evolving fields. It might be what's going on here, but I haven't dig too deep into what's going on there. But really, we wanted to kind of stress test this emulator a bit more and see how it responds to different forcings, just like kind of we would do with traditional climate model experiments. So we've taken the emulators and we've trained them on this reanalysis forced ice ocean simulation, kind of a present day forcing, and then we're going to roll them out using atmosphere and ocean conditions from a PI control run and also 1%. And you can see here that the FlowNet's still doing a good job there, capturing that spatial pattern of sea ice thickness. Maybe it's slightly biased high. It's got slightly too much sea ice thickness here, especially over into this kind of eastern side of the Arctic. And then the full state model generally has just like a wrong spatial pattern. It's got ice too thick extending into kind of Fram Strait and north of Svalbard area. And then in the 1%, this is averaged over about 140 years of a 1% run. So this does go ice free at the end of the run. We'll see in a sec. Looking at some time series, we can see some interesting behavior. Both the emulators are slightly biased high. This in the PI control run, that's the solid curve here. So the orange is the coupled model. This is CM4, and then the emulator FlowNet in black, and then the full state model in gray. So the FlowNet's doing slightly better, but still a bit biased. And then in the 1%, we are missing the kind of early trend and have a slight bias in the early run, but we kind of close in on the numerical simulation towards the end of the run. And just to decompose that into this is annual mean again. So looking at what's going on in, like, for example, Arctic summer and winter. We do go ice free around to 290 in this run. But yeah, there's some rapid decline in the numerical model, which we're not quite capturing with the emulator there. So that's definitely some room for improvement in future work there. And in the Antarctic, it's arguably doing even better. You know, in terms of the PI control and the 1% run, we're pretty close to CM4 there, and especially if we look at the 1% run in for example February, the FlowNet model is doing much better at tracking the CM4 run, whereas the PI, the full state model, sorry, is biased too high in summer there. So I just wanted to dig into this this sea ice variability metric a bit more. So these plots here are showing anomaly correlation coefficients for annual mean sea ice volume and or detrended annual mean sea ice volume at each grid cell. This is in the 1% run. So we can see FlowNet is got really high anomaly correlation coefficient with CM4, and then the full state model still has good correlation, but slightly less. And what's pretty impressive, I think, is if we look at the mean sea ice volume anomaly time series in this rollout, that FlowNet's really, it's nailing that interannual variability in volume, even though it was trained on a reanalysis force simulation. So it's a kind of a real held out test case, and is doing well there. And yeah, in the PI control run, similarly doing really well at 0.96 there. And what's nice about this formulation of the emulator in this kind of mass budget sense is we can decompose those anomalies into their thermodynamic contributions and the export-driven anomalies, just to check, is the emulator getting the anomalies correct for the right reasons. So we can see the orange curves here are our CM4 anomalies, and then the black is the emulator. So you can see for where the CM4 has an export anomaly, then the emulator is getting that same anomaly as well, and similarly for the thermodynamics. So it looks like it's learned to attribute where anomalies should be driven by export versus thermodynamics, which was nice to see. So this is my last slide, and I realize I'm about out of time, so I'm just going to say that we've built this emulator with coupling in mind, thinking about coupling it to atmosphere and ocean emulators. So it's also outputting related variables for that, like ice ocean salt fluxes and top and bottom melting energy fluxes and so on, and it seems to capture the kind of spatial variability of those, and also their kind of mean seasonal cycle as well. So yeah, so a few more things to do in the future, couple it, and also work towards energy conservation and so on. But I'll stop there, and I'll leave this up if anyone wants to know what input variables are. I tried to look through the CMOR list in case people wanted to get a standard diagnostic set of variables that we're using, but I'll stop there. Thank you.
Excellent. Thanks. Let's see. Any questions for Will?
Actually, I'm going to stop sharing because I can't see anyone.
Okay. Yeah. We have a line. Jo, you want to go?
Yeah, very impressive work. It seems compared to the full state model, FlowNet slightly underrepresents the year-to-year variability. Does it have the common issue with same as other machine learning based models tend to underestimate extreme cases?
So yeah, just to check what you mean. So the full state model was the one with less variability, and whereas FlowNet was getting the variability really well. But I think we do see that in various models. For example, in this in the Samudra Ocean emulator, that's a kind of subject of ongoing work in the fact that it doesn't really capture much of the ocean variability in critical regions, like some of the kind of western boundary current regions. And I think that there's some issues with out of sample behavior with that emulator, but I think people are working on it and trying to find ways of treating the input data in terms of normalization and different flavors to the architecture to try and address that.
Thank
Cool.
you.
Yeah. I think Cece had a comment first, or
I have a question. Hi. Do you emulate the temperature and albedo and all of the variables you need to couple to the atmosphere, I guess is the real question.
Yeah, so we're emulating the ice surface skin temperature. That was just one of the plots at the end I kind of rushed over there. The albedo, I'm not emulating at the minute. We did think about that. there was a kind of issue with it in terms of the albedo diagnostic out of CIS is I don't know how representative that would be. I mean, it's only defined where like incoming shortwave is greater than 0, so it just the diagnostic is set at a fixed value of 1 during like polar winter. So I don't know. Yeah, I don't know what we would do for that in those cases. So
Okay,
Okay.
thank you.
And then Alec had a question.
Yeah, forgive my naivety, but my kind of baseline assumption would be with this kind of work, the sophistication of your sea ice model is going to determine how well this emulation performs. And so if you increase the physics and sophistication and the parameterizations, it's maybe going to be harder for an emulate to copy that and work in different climates well. Is that kind of how you see things? Like what's the level of kind of physics included in your model? And if you add more schemes, how much are you expecting it to still perform as well?
Yeah, that's a good point. I was thinking of that same question earlier when it's looking at all of these things like the impact of lateral melt and growth parameter, and like the impact it has on it. I was like, oh, I wonder what that would happen if.
There's infinite things we can do here.
Yeah, I mean, we've basically just tried to constrain some of the CI dynamics and thermodynamics based on some of the like simple assumptions about how we expect the sea, like the what goes into like the 2D momentum equation for sea ice, and making sure that we've like got the appropriate forcing variables to constrain the dynamics in that way. And so I think you could go deeper and try and incorporate a lot more physics into these things. And I think we'll probably look into some of that stuff when we're thinking about things like energy conservation. But I think overall, in terms of to get the kind of bulk evolution of sea ice, and I think it's you can do it pretty well with just the kind of standard dynamics and thermodynamic forcing variables that you expect to. Yeah.
Is it quick?
And never mind.
Okay.
Sorry.
Okay, I think we need to move on. So now Lingwei Li is going to present on the microplastics project that she and I have been involved in. So you want to sit here? Or... Sure.
So are you going to present on this computer, right?
Yeah.
Okay.
Yeah, well, you can find the presentation. So my name is Lingwei Li, and I'm a postdoc at CU Boulder working with Alexandra Yang. So our modeling group, project modeling group, put a lot of efforts on modeling microplastics in the CSM2. So today I'm going to have a short report.
Oh my gosh, I'm so sorry.
No, good. Okay, take your time. Arctic sea ice ocean exchange of microplastics in the CSM2.
I'm so sorry. I need to go. Sorry, guys. I'm just trying to find this
I think I
document here.
Upload.
Yeah, we've already downloaded in it.
Okay.
Okay, sorry. Yeah.
Yeah.
Yeah. No, sorry. Oh gosh. Technical issues. Yeah, that's not my question. It's okay. It's next. So sorry. Okay, so I'm gonna share. Here, how can I find that?
Window. Are you entire screen now? Yes.
Yeah, that's what I did it first.
And then just present.
Excellent.
Okay, can you see this? Okay, sorry.
Yeah, we could put it in the slideshow mode. It'd be great.
Yep. Here we go. Hey.
Hopefully it works.
Yeah, it doesn't look nice. Yeah.
And maybe if you can hide the thing at the bottom too.
Yeah, this one.
Awesome. So we may hear a lot about microplastics lately. microplastics are now pervasive in global oceans, and by definition, microplastics are any particles smaller than 5 millimeters and varies in colors, shapes, and density. When we think about large accumulation of microplastics, our minds immediately go to the subtropical jars, the North Pacific, North Atlantic, these well-known garbage patches. But recent studies found that microplastics are found even in the remote Arctic region. And available observations show that the concentrations of microplastics in the Arctic sea ice are 1 to 6 order of magnitude higher than in underlying Arctic Ocean. But the reason for its high concentration in the Arctic sea ice are still a mystery, and relatively few modeling studies have focused on this microplastic problem. So this talk is really guided by 3 questions. What the role of sea ice formation melt in enriching Arctic sea ice microplastic concentrations compared to the underlying surface ocean? Does microplastic transport by sea ice affect the microplastic concentrations globally? And does variability in ocean microplastic concentrations affect microplastic concentrations in the sea ice? So to answer this question, we use the sea ice and ocean component of CSM2, where microplastics are added as passive tracers. There are 2 tracers, neutrally buoyant microplastics and positively buoyant microplastics, and the buoyancy only affects the tracer movement in the ocean. The model is forced by JRI-55, and the microplastics is forced by the worldwide coastal plastic with input data in proportion to the population density, coastal population density. We are not modeling negatively buoyant microplastics because these particles could rapidly sink to the bottom and will not reach to the Arctic where they interact with the sea ice. So, well, currently, how much microplastics are taken up and released during ice growth and melt is poorly understood. As a result, their parameterizations in the model remains weakly constrained. So following previous modeling work for aerosols, we set up 3 factors to play around. The optic factors for microplastics during fragile ice and basal ice growth, and release factor during top ice melt. And what we assume all microplastics get lost during basal ice melt. But for the initial control experiment, we just set optic factors equal to 1 and release factor equal to 0. So this means the concentration of microplastics trapped into sea ice is same as the surface ocean concentrations, and there's no surface melt release for microplastics. And by the end of simulation, the total microplastics in these control experiment show overall good agreement with ocean observations globally, reproducing these 5 major garbage patches right now. Now let's switch gear to see what happens in the Arctic. So here I'm showing the ratio between the sea ice microplastics and ocean microplastics. For neutrally buoyant microplastics on the left and positively buoyant microplastics on the right. And we can see for most regions in the Arctic, the ratio is larger than 1 and can be as high as to 60. So this means the model can really reproduce higher microplastic concentrations in the sea ice than in the ocean, which is really consistent with observations. To provide insights into the parameter space, we did a series of sensitivity tests to explore the factors. So specifically, we changed both factors from 0 to 3. And here is showing the mean ice to ocean ratio in the Arctic region for 3 factors from 0 to 3. And we can see that the model responds linearly for both optic factors. Increasing basal ice optic factors could lead to enhanced ratio by a factor of 5, while doing the same thing for fragile ice, only increases the ratio by 50%. So this is basically because the fragile ice contributes much less for Arctic sea ice formation in the model. Also, the model responds nonlinearly to the surface melt release factor following the exponential decay pattern, and this is because the surface melt release factor is a function of sea ice microplastics concentrations. So overall, we still see the ratio is larger than 1 when the release factor increases further to 3. So this means that the higher uptake factors is not what causes the increased microplastic concentration in sea ice compared to the surface ocean. Now, to answer the question, how microplastic transport by sea ice affect microplastics in the global oceans, we performed additional experiment called no uptake case, which does not simulate any microplastics get trapped into sea ice. So there's no uptake and release factors at all. And these maps are showing the percentage change in the ocean with upticks relatively no upticks. So blue means reduced microplastics, red means increased. So the top panel is showing the sea surface ocean change, and the bottom is showing the vertical integral of the whole water column. So we can see basically there's roughly 30% decrease in microplastic concentrations in the Arctic Ocean and a relatively small increase in the North Atlantic. The decrease in the Arctic region is not surprising because they are now get trapped into the sea ice, and the increase in the North Atlantic is basically driven by the differences in the microplastic transport pathways between the sea ice and ocean. Last but not least, we may wonder how ocean distributions of microplastics relate to the microplastics in the Arctic sea ice. So we have two additional experiment. One is called release case. This is a more realistic case with both uptake factors and also the sea surface release factor. Top ice melt release factor. Another one is called constant ocean MP case, where ocean microplastics are spatially and temporally constant, but we still have the same uptake and release factor as release. So to compare these two cases, we calculate the annual mean total mass of microplastics from 1970 to 2017, and we get this time series determined as most using 5-year block averages, as shown on the right. The top is for the neutrally buoyant microplastics, and the bottom is showing the positively buoyant microplastics. And we can see a very similar temporal variability in two cases, with slightly larger amplitude for constant ocean MP case. So that means the variability in sea ice microplastic mass is strongly related with sea ice thickness instead of the ocean variability microplastics. So to sum up, the model can really reproduce higher microplastic concentrations in the sea ice. The major takeaway message is that although we are not yet able to answer why the model is able to reproduce higher microplastic concentrations in the sea ice than in the ocean, we are ruling out two potential causes for driving enhanced microplastic concentration in the sea ice. One is higher uptake factors, and the second is the ocean distributions of microplastics. I also analyzed seasonal and interannual variability of microplastics in the sea ice and ocean, so feel free to reach out if you are interested. I finally want to thank our entire MESO group for valuable discussions and guidance and support. So that's all about the microplastics. Any questions are welcomed. Wait for a while.
Any questions? David, yeah.
Yeah, I have a question about the sea ice microplastic data, which I know is not the focus of your talk, but I was wondering, like, how standardized are the protocols for actually quantifying it? Because I guess my sort of very, very anecdotal observation is that if you see something like microplastics, you definitely report it.
Yeah.
But if you take an ice core and nothing's in there.
Yeah, well, we do have a data set for the ocean microplastics like here, but we don't really have spatial maps for the sea ice microplastics. So we only have some numbers in the Central Arctic and near the Greenland Sea, but we don't really have like big data set platform for the sea ice microplastics. But yeah. But the ocean is only, the model is only first by the ocean microplastics.
Yeah.
Yeah.
Other questions? Yeah, Sky.
While we're on this slide, I know you also focus on the Arctic, but I was curious if you have thoughts on this disagreement in the Antarctic between the observations and your control run. It seems to be pretty.
Yes. For the control run, we only set uptake factors to 1 and no release factor. So this control run can be estimated as the upper bound of microplastic in the ocean and also in the sea ice. And we don't really have much observations in the Southern Ocean. So also we don't really have much input flux in the Southern Hemisphere. So we don't really have much concentrations right here. Did I answer your question?
Yeah, I guess in the future, would you then force in the Southern Hemisphere and just see what happens? Like maybe would you expect better agreement?
Yeah, also for the input flux, we don't really have open ocean data, such as the microplastic from the shipping, and also what else from the open ocean? Biofouling is not also included, so there's a lot of things we could do in the future.
Yeah, there are definitely some missing sources. There could be like atmospheric deposition, which is probably stronger in the Southern Hemisphere, I'm guessing. And also the design and the experiments, there's some questions about maybe the plastics are not quite spun up enough. So that could be part of it. Yeah.
Thank you.
So great. Okay, other questions, quick questions? Okay, great. So our next speaker is Jo. She's online. I think you can share yourself. Stop sharing.
Can you see my slide okay?
Yeah, looks good.
Thank you. Okay, here I will talk about X Typhoon Halong, which was which originated from the tropical western North Pacific as a typhoon, and induced severe flooding over western Alaska. This presentation is based on the paper led by my student Mingshi Yang, which was recently submitted to BAMS. I want to acknowledge our funding agency, Office of Naval Research, and also my collaborators, including Alice. Okay. As I mentioned earlier, Halong originated as a typhoon over western North Pacific, as you can see in the figure in the lower left. It propagated over regions of warm SST and then re-intensified south of the Bering Sea, and later it induced severe flooding over western Alaska. This figure shows the intensity evolution of Halong. We can just focus on the black curve here, which is sea level pressure from EIA5. The shaded areas represent two re-intensification episodes. The second one is more persistent than the first one, and it led to the peak intensity of Halong on October 12th. So in this presentation, we are going to address the following questions. First, what factors or processes contributed to the extratropical re-intensification of Halong? And how does Halong compare to other Arctic cyclones near the Bering Sea? First, I will show the role of upper level forcing and the contribution of warm SST to the re-intensification. Then we will take a brief look at the climatology of Arctic cyclones that originate from the tropics. Okay, first, upper level forcing. Hide this. This slide shows the evolution of sea level pressure in purple contours, 300 millibar geopotential height in black contours, and precipitation in shading. Halong is located at the center of Ichi Plateau domain. You can see to the north of Halong, we have a strong extratropical cyclone. It has a deep circulation structure, which steers Halong cyclonically around its circulation. If you look at the precipitation field, you can see Halong later develops a frontal feature extending from the near the center of the cyclone southward and westward. Now let's look at the evolution of vertical velocity. The top row represents the first re-intensification episode, and the bottom row represents the second re-intensification episode. The first column shows omega from ERA5, and the second and third columns represent omega derived using the QG omega equation. The second one is related to the convergence of the Q vector, or we can call it adiabatic QG omega. And the third column represents the contribution from the diabatic heating, or we can call it diabatic QG omega. During the first re-intensification episode, you can see the contribution of diabatic heating is dominant. Panel A and panel C have very good agreement. During the second re-intensification episode, both the Q vector convergence and the diabatic heating make a strong contribution to the total omega field. Next, we are going to focus on cross-section going through the center of Halong. Again, I want to highlight the extratropical cyclone to the west of Halong. As I mentioned earlier, Halong moves cyclonically around this massive extratropical cyclone. During the second re-intensification episode, it is to the east of the extratropical cyclone. In this figure, shading represents the vertical cross-section of vorticity related to Halong. We can see a slight vertical tilt. And the purple contours represents wind speed. We can see an upper level jet with a maximum wind speed exceeding 80 meters per second. And that induces vertical wind shear. And the vertical wind shear leads to cyclonic vorticity advection downstream of Halong and anticyclonic vorticity advection upstream of Halong. And based on the QG omega equation, the cyclonic vorticity advection by thermal wind is associated with QG lifting, which promotes upward motion, and that is further amplified by diabatic heating or precipitation. Now let's look at the contribution of SST. Here we carried out 3 sets of experiments using WRF model. In the first experiment, we use SST from ERA5 to drive WRF model, as represented by panel A here. In the second experiment, the model is driven by long-term mean SST in mid-October during 1940 to 2025, as represented by panel B here. And in other words, we have removed the SST anomalies shown in panel D here. In the third experiment, we used the detrended SST, and the SST trend is showing the lower right panel. And you can see the SST trend is much weaker compared to the total SST anomaly field. For each experiment, we have 18 ensemble simulations with different model physics. This figure shows the track of the storm on the left and the storm intensity on the right. You can see the storm track does not differ much between experiments. In other words, the SST modifications do not strongly affect the track of the cyclone. In the right panel, we have intensity from different experiments. The gray line shows the control experiment along with the ensemble members in thin curves. The red one is the model driven by detrended SST, and the green one is the model driven by the long-term mean SST. The blue one is EIA5. All the simulations overestimate the storm intensity, but here you can see compared to the control run, the cyclone intensity in the two sensitivity experiments is much weaker. That can also be illustrated in the box plot on the right. Here, the three groups represent the control experiment, the long-term mean SST experiment, and the experiment driven by detrended SST. Again, in the two sensitivity experiments, the cyclone intensity is significantly weaker than that in the control experiment. Especially in the experiment with long-term mean SST, you can see the substantial weakening of the storm intensity. Then how does the SST affect the cyclone intensity? Here we show the time pressure evolution of temperature in contours and specific humidity in shading with respect to the control run. The top panel shows the experiment driven by the long-term mean SST. You can see we have negative values in temperature and also specific humidity. In other words, the warm SST anomalies help to enhance the column specific humidity and also help to warm the lower and the middle troposphere. With the warmer lower troposphere, we have reduced static stability, and the reduced static stability and enhanced column water vapor precondition the storm for re-intensification. In the lower panel, we have the experiment driven by detrended SST. We see similar signals, but with the magnitude is much weaker. Okay, now a quick look at the climatology. Here we show Arctic cyclones in the North Atlantic sector in some parameter space. Here in both panels, the x-axis shows the maximum cyclone intensity. In the left panel, the y-axis shows the maximum intensification rate. Here we just focus on the mid-latitude sector, even if the cyclone originates from the tropics. You can see, I should also mention the shading and the numbers represent the sample size for each beam. You can see most cyclones cluster in this region with the intensity around like 987 millibar and intensification rate less than 1 hectopascal per hour. The red mark here represents Halong. It is characterized by strong intensity and also rapid intensification. The intensity and the intensification values rank top third and second percentiles respectively. In the right panel, the y-axis shows the latitude of maximum intensity, and Halong is slightly north of the median. In addition to Halong, we also have X typhoon Ampule in 2024 and Merbak in 2022. In particular, you can see Merbak, which is in green mark, is even more intense than Halong. Okay. As I mentioned earlier, latent heat release is important for the re-intensification of halon, and that is tied to moisture content. Now let's take a look at the moisture field. What we see here is the cyclone-centric column water vapor. The first panel shows all cyclones during 1940 to 2025 in the warm season. We can see a moist tongue east of the cyclone center. The second panel shows the difference between recent decades and the earlier decades. We can see prevailing positive anomalies or positive differences, which is consistent with warmer atmosphere and higher water vapor holding. Halon is shown on the right. We can see a clear moist tongue resembling either a warm conveyor belt or atmospheric river. In particular, the red contour outlines the region where the column water vapor exceeds the 90th percentile among the big cyclone population. In other words, Halon is characterized by high moisture content, which may be related to his tropical origin. Okay, this one shows the seasonality of Arctic cyclones that originate from the tropics or polar equator world of 30-degree north. The black line shows the long-term mean from 1940 to 2025. We can see a bimodal distribution. One peak in later winter, early spring, and another peak in late summer and early fall. The blue bars and orange bars represent the early period and the recent decades, respectively. For the blue bars, which is 1940 to 79, you can see the primary peak is in February, late winter. But in recent decades, the peak actually shifts to early fall and late summer. In particular, you can see in September we have an increase by about 4 times compared to early decades. But this, even with the increase, I should emphasize, Arctic cyclones of tropical origin are still relatively rare. For example, in October, you can see the mean frequency is less than 1 per decade. So Halon is a rather rare case. Okay, a quick summary. Warm SST anomalies preconditioned Halon's re-intensification by increasing column water vapor and reducing static stability, and QG lifting associated with the cyclone interaction with another extratropical cyclone led to the rapid deepening of X-Halon south of the Bering Sea. The frequency of Arctic cyclones of tropical origin has increased in the recent decades. For example, in September, we have a factor increase by a factor of 3. Given the role of SST in cyclone intensification and the destructive impacts of cyclones through storm surge, coupled models would be useful tools in assessing future changes and the impacts of such cyclones. Okay, I will stop here. Thank you.
Thank you. Any questions? Yeah, Courtney.
Thanks for a really interesting talk. I'm just curious if you have a sense, I imagine you don't, of the biogeochemical impacts of the changing storm distributions. I imagine I can hazard guesses, but I'd be very curious if you have looked at that at all.
Oh, sorry, I have no idea. I would love to learn your thoughts.
Thanks.
Other questions? Thoughts? Okay, well, we'll try to, we're a little behind, but I'll try to keep it moving here. So next up, we have David Clementswell, who's going to...
Y'all should feel free to move up. This screen is really hard to see. I know that if I sit back there, I cannot read anything on this screen.
I'm gonna.
We're afraid.
I'm gonna.
We're afraid of you. We need to stand far away.
What was that?
We're afraid of you.
I mean, I did like up until this morning, but I don't think it's felt that bad.
Let me see if I can adjust it a little bit.
Not moving.
Use like
Detail graphs, we need to see all that.
You know, I tried.
Vicky, isn't that the first question that comes to your mind? What's happening with the biology chemistry?
Yeah. If you want to know who these people are, you definitely need to be close enough.
all right.
Oh,
That should be a little better, I think.
Yeah. I'm just taking up more space than I need.
All right. Good to go?
Yeah.
Okay, thanks everyone for being here. I know it's a long day. I know I might nod off during my own presentation, so sorry about that. Before I begin, I want to acknowledge that the work I'm presenting basically rests on the shoulders of many people. So I'm going to present work that is from both combining sort of efforts within the CESM project, the SEIS consortium, the Mosaic expedition, and the recent Contrast expedition. And all of these activities, whether large-scale modeling efforts or large-scale field campaigns, rely on more people than could fit on this screen. So I really appreciate the community and the communities, I should say, that make this kind of work possible. So I'm going to talk about melt ponds, specifically on Arctic sea ice. And this presentation essentially has two things sandwiched together. Alice asked me to give a brief kind of refresher on sea level ponds and why we've done that. So I'm going to kind of rush through that, but please come talk to me afterwards. And then I want to spend most of my time talking about the properties of ice under melt ponds in recent observations and kind of where I think models might want to go in the future. I'll begin with just a quick background on what is a melt pond. So melt ponds are puddles. They form on the surface of Arctic sea ice every summer. In horizontal dimension, they vary from 1 meter to about 100 meters. The photo in the upper left here that those in the back can't see has a ship at the very bottom of it. That's the length of the football field plus end zones. And in terms of depth, most melt ponds you could comfortably walk through if you had tall boots or hip waders. Exceptional melt ponds you might want a dry suit or have to swim in. They are a ubiquitous feature of the summertime Arctic sea ice, and they're important for a whole bunch of different reasons of the system. As physical scientists, I tend to think most about their impacts on the optical properties, so this is the albedo and the transmittance into the upper ocean. The photo on the top left here is Nora and Savannah making albedo measurements over a small melt pond this summer. The photo on the right is looking from underneath the sea ice using these ROV. And the bright patches from underneath the ice are the melt ponds. So the dark patches on the surface are the bright patches underneath. They also have important impacts for remote sensing retrievals and on ice navigation, as well as the marine ecosystem. And we've actually known quite a bit about how melt pond physics works for a long time. In the sort of classic presentation, which is from Hayo Aiken and others' work back on Shiba, is that ponds start when meltwater pools in depressions. Those depressions rapidly deepen below sea level due to essentially preferential surface melt under the darker pond. And within about 3 weeks of those initial ponds forming, you get connections to the ocean, whether they're macro scale flaws or the ice itself becomes porous enough that the ponds are hydraulically collected to the ocean, and they spend the rest of the summer more or less with their surfaces at sea level, at least for most ponds on most sea ice. And the sort of remarkable fact about this is that when we look in high resolution satellite and airborne observations, the pond fractions for this stage 3 sea level phase stay very consistent. They're within a band of about 15 to 40% of the surface area of the ice. And I can go into reasons sort of theoretically why that should be the case. But in terms of modeling ponds, it's a very convenient fact that they remain in this relatively narrow band. In contrast to the melt pond fraction, melt pond optics are highly variable. So you can just see this, if you're flying over the ice, you will see on the flow scale, so on scale of tens to hundreds of meters, considerable variation in apparent optical properties of ponds. We can also see this quantitatively, such as this figure showing spectral albedos from ponds in the blue curves down here from Bonnie Light and others back on the IceCaves cruise. And generally speaking, we think multi-year ice ponds are brighter than first-year ice ponds, and thicker ice under ponds leads to a brighter pond than first-year ice, or sorry, than thinner ice. So, Alec, I think you're going to talk a lot more about how melt ponds do in CSM, so I'm going to do this quickly. Compared to field observations, melt ponds in CSM2 were both too extensive, they covered too much area, and they were too bright. They had too high of an albedo. And remarkably, or maybe not remarkably, depending on how models are tuned, the grid cell mean albedo actually is extremely consistent with observations. So you say, David, what are you going on? What's wrong with you? You got your grid cell mean albedo right. Well, I think these are still potentially a problem. So first off, we don't know that these errors will offset in different sea ice states, right? They may not offset in the future. They may not have in the pre-industrial, actually. Second, you know, I know there's folks in here who are interested in data assimilation. You can't do that if you need these offsetting errors to balance. And then third, I'll encourage everyone to remember that albedo isn't the only optical property to think about. Transmittance is really important for light in the upper ocean, and you can have the same albedo with very different transmittance. And so we set out in our new pond parameterization basically with 4 objectives. We wanted to make the ponds more physically realistic. We wanted to have much better alignment between observations of melt pond fraction with the model. We wanted the albedo, of course, to be better. And ideally, we could make those 2 latter changes without creating our grid cell mean albedo that we were so happy with. In this short talk, I'm not going to go into the details of how we've done that. I'd encourage you, if you're interested, to come talk later. The parameterization is in SEIS and IcePack, albeit the documentation, as I have learned from conversations with some of you, might need some updating. But the 2 changes we made, one, we made a change on the optics that was aimed to allow shallower ponds to still optically behave like melt ponds. And so they are, relatively speaking, darker than what the prior parameterization was doing. And secondly, as Alice mentioned earlier, we included a slightly more physically based pond area and depth evolution that allows the pond surfaces to sit at sea level. We've tested this not as much as I would like, but in a variety of contexts. We've tested in standalone single column model runs, comparing directly with the mosaic observations, where we can really isolate the sea ice physics. The new parameterization performs substantially better than the old one. We've also tested in standalone global SEIS runs. What you're seeing here is basically the change in ice thickness when we change parameterization. Thanks to Dave Bailey for running this, and we've seen basically no change. So we haven't changed our grid cell mean albedo. Standalone ice runs, we don't see a big change. However, when we go to fully coupled runs, we see much bigger changes. And again, thanks to Dave for running these simulations. These are in an old version of CSM3 development run, so I wouldn't take any of the numerical values here pretty strongly. But in general, in these runs at least, we saw thinner sea ice in the coupled model with the new parameterization, and considerably more light in the upper ocean, suggesting that possibly a feedback with solar heating of the upper ocean is important. So what I want to talk about in the remainder of my time is some recent work I've been doing looking at the properties of the ice under melt ponds. And the first thing you might want to know if you're asking, well, what is the ice under melt ponds like, is what's its thickness? How does it compare with the ice not under melt ponds? In general, ice under melt ponds is thinner than the ice not under the ponds, right? The water tends to pull in depressions, and it tends to preferentially melt in those places. And it could be, but at the the kind of coarseness that we apply the ITD, in a general ITD thickness category, you have considerable overlap between the ponded ice thicknesses and the unponded ice thicknesses. And so this is just showing an example, courtesy of Max Ringel at Bremen from the contrast expedition this summer, where the yellow bars are the histograms of ice beneath ponds and the blue bars are the histograms of ice not beneath ponds. And you can see that there's considerable overlap in these distributions, and they, most of this data is falling within category 1 of our ITD, right? And so we need basically a subcategory parameterization to do this well. Another difference that I haven't found reported nearly as widely in the literature is that when we take ice cores out of ice and ponds, the pond ice is actually considerably less saline and less dense. And so that means that ice has already released much of its salt to the ocean, which is not something we currently represent in the model. And we can talk afterwards about remote sensing retrievals, but knowing your ice density is pretty critical if you want to go from an altimetry retrieval to ice thickness. And I'm not sure, to be honest, how well one could model these changes in salinity and density if you didn't independently model the ice under the ponds. Susie, do you have a question?
You mean it's bubblier? Because if it's less brine, then if it's less dense, is there air in it?
I think so. I think there's more, yeah. There are more bubbles. These were densimetry measurements. So this is Archimedes' principle weighing the ice in kerosene. That said, there's some questions about technically how you make these measurements. I've got some samples on their way to Switzerland that I would love to have funding to actually try out some different techniques for measuring. But yeah, thanks for the question. All right, I'm running short on time. Sorry about that. I want to finally come back to this question of melt pond optics and look a little bit about why do we see such a dramatic spread in the apparent optical properties. And so I really like this example from Bonnie's work, where Icescapes was driving around the Chukchi and Beaufort Seas and seeing this much variability. It turns out you can actually see similar amounts of variability within the same melt pond. And so this is an example from the contrast where on the left here, I'm showing albedo. There was a light portion of the pond, which is closer to the camera. That's shown in the blue curves. And then a dark portion of the pond, which is kind of the rest of the pond, further away from the camera, which is shown in the orange curves. And you can see is that the spectral albedos in the visible are about double in the bright portion than in the dark portion of the pond. And then there's correspondingly differences in transmittance as well. You might say, well, is this the depth of the pond, right? It's water depth? No, actually, the brighter portion has deeper water. We don't have a big difference in our ice thickness here, but we do have differences in the density profile. Notably, as Susie suggested, we have lower densities deeper into the ice, which is suggestive that there are bubbles there. And these are core photos and vertical thick sections and cross-polarized thin sections. You won't be able to see it from back there, but there are indeed more bubbles, particularly in kind of this layer of the light portion of the pond. And the ice microstructure plus kind of the overall context suggests that this is actually deformed ice. And so potentially deformed ice where you've buried the snow is a reasonable mechanism to have a much brighter pond. I'll also mention we've gotten a chance to study multi-year ice and first-year ice where we had more or less the same ice thickness under the pond. And again, we actually see a very dramatic difference but in the spectral albedos. So the multi-year ice is almost double, not quite double, in the visible from the first-year ice. Again, similar ice thicknesses. Big difference here again is bubbles. In this case, it's probably not deformation because we have data on the ice microstructure. But if you look really closely, you can actually see within the crystals in the multi-year ice, there are bubbles incorporated. I think that's really cool and something we should think about how that would be represented in a model. Just in summary, the sea level pond parameterization is available in SEISS. If you use it, please feel free to talk to me. I've really enjoyed the discussions I've had with people. I'll also mention that the T-scale pond drainage parameter needs to be set lower in running with it. The default is from the level pond parameterization, which is just too high. We plan to do preliminary tests, we plan to do further tests in CESM3 once we have a workhorse simulation. And then finally, I think there's potential to essentially use physical evidence from the ice beneath melt ponds to get a better understanding of the variability that we see. But if we wanted to eventually translate that learning into the model, we might need to consider separately representing the thermodynamic evolution of the ponded ice columns. And that would be a major shift in how we do with the model. Yeah, thanks all for listening.
Some quick questions for David while I switch over.
Maybe really silly one, but I think my brain glanced over maybe something that's important. When you're saying the albedo is higher for the deeper ponds, you're talking about the ice albedo, or you're talking about the surface albedo? Does that make sense?
It's the albedo we measure from up above the pond. So like we had deeper water, and yet the albedo was higher.
Why?
Because the ice under the pond is what it's important for the albedo, not the water depth itself.
Wow, that's so
Always outrageous when observations.
All right, another quick question for David. Anything? Going once, going
You can
twice?
talk to me later.
All right, okay.
Moving without me.
It's moving out of.
Alex is all done.
So,
Is that like slideshow mode thing?
yeah, apparently, you can probably get out of that. But anyway, our final speaker of the day, Alec Petty.
Yes, I'm not Maddie Smith. I'm Alec Petty. Maddie couldn't make it. Unfortunately, she's on some exciting fieldwork somewhere. She was hoping to join remotely, but I think she also wasn't able to do that too. Anyway, we've been working closely together on this project, so I hope I can do a decent job at summarizing some of these ideas. The last couple of years, I've given talks about freeboard and thickness and evaluating CMIP6 models. We're still very much interested in that, but we have this new project that's much more focused on melt ponds and seasonal feedback, some of the ideas that David just mentioned in a newly funded project. So we're just coming to end of year one. So this is kind of our first step at kind of looking at some of the basic questions of how do these models actually represent melt ponds and can we do any more fun science with them? So I think David showed this same plot. There's been a little bit of work already in trying to kind of assess how well the models do at simulating melt ponds, especially this nice paper by Melinda Webster and others. This was obviously a little bit more focused on how well the models represented these in situ campaigns. There hasn't been a huge amount of work, kind of virtually nothing really, that's doing similar comparisons at more basin scales. I think mostly that's just because there hasn't been the observational data there to do that. But there has been some newer data sets that have been recently put online and included in the literature in the last couple of years that I think do maybe enable these broader basin scale assessments, which I think is quite exciting. So there's a few different observational data sets that are out there. You need to use them with caution, but we're trying to do that as best as we can. Our primary data set we're using is this MPV2 data set by folks from the University of Bremen. It's based on the Sentinel-3 optical imager, OCLI. If you just kind of eyeball this, what we've done here is we tried to produce we're kind of doing a similar thing to what we did with our ISAT2 work, where we're looking at very like modern era kind of mean climatology, 2017 to 2025 in this case. And now we're looking at the mean for these kind of 4 key melt pond months. There's a lot of missing data in these data sets. these, as I said, this one's based on optical imagery, and so clouds just complicate this. They can cause issues with the retrievals, so a lot of the data is flagged as uncertain or unclear, and a lot of it's just missing because of clouds. So when you do this kind of aggregation, we have to do this ourselves in a little bit of correspondence with the data set producers, but you can start producing maps like this. So if you eyeball this, yeah, we see this nice progression of the melt ponds as we move through summer and with some strong regional variability. There are some other data sets that are floating out there. There's another, the two that we're aware of are both based on MODIS. We don't have a good name for one. I think it's from some Chinese scientists and another one from some scientists at CPOM. They tend to produce pretty similar regional and seasonal distributions. But the CPOM product especially has even more reduced spatial coverage. Again, I think there's a lot more filtering of the data based on clouds, and they both have more limited temporal range. In terms of the models, we've been kind of interested in understanding what we can do with the CMIP6 models and also the CSM2 large ensemble. And again, this is maybe something that people don't know, but there are these melt pond outputs that are available in the CMIP6 archive, which haven't really been exploited yet to our knowledge. So our research has found 5 models that produce outputs of melt pond distribution, mostly coverage, but I think maybe volume too. And then also the CSM2 large ensemble. And they all use the exact same version of SEISS, but they use 2 different melt pond schemes, which is kind of nice. So we have the levelized scheme that David mentioned, and then the topographic scheme. I'm not going to go into the details about the model physics, mostly because I'll do a terrible job of doing that. But yeah, I think the basics are the topographic scheme. We see this melt pond water accumulate into kind of topographic lows. So it's based on the ice thickness distribution and a conversion of that into a kind of relative height measure to do that distribution. The levelized scheme is maybe a bit simpler, and it's more based on the level ice versus deformed ice fraction within grid cells, and melt ponds form only over the level ice, not the deformed ice. As I said, we've been kind of engaged with work trying to assess CMIP6 models. It's hard to see this plot on this screen, but this is the kind of plausibility matrices that we've been putting out, where we're assessing the sea ice area, freeboard, and thickness from ISET2. The point being, we've kind of reproduced this plausibility analysis with that 6 model subset, and the performance is pretty similar to the CMIP6 ensemble mean, which is nice. So we're dealing with a subset that at least is somewhat representative of the wider CMIP6 ensemble, we think, at least in terms of those metrics. But this is now what they look like in terms of the melt pond concentration. So that top row is showing the same observational data set I showed a few slides ago. And then the bottom row is now showing that 6 model ensemble mean for those same months. So if you eyeball this, you're like, okay, this looks pretty good. We've got low concentrations in May. Things go up as we move through summer. But I think we can all kind of see some interesting regional differences and potential biases, which is what we want to explore more. If we first just plot the hemispheric, just Arctic mean melt pond area in the models and observations, we get plots like this. So the black line is the observations from the MPD2 data set. We try to characterize a kind of basin scale uncertainty based on our interpretation of their quoted uncertainties. Then the red line show the different model results. We've sorted this by the topographic schemes in the top row and then those levelized schemes in the bottom row. And then the plot on the right there is showing the same thing, but aggregated based on the 2 different melt pond schemes. So we can see that the topographic schemes tend to overestimate the melt pond coverage in June and July. But the levelized schemes seem to kind of do the opposite. They seem to have a bit of more of a delayed onset of melt pond development, but then there's stronger peak potentially. But yeah, I don't know. The takeaway from this is that they're not doing too bad, right? But if you look at regional differences, maybe then things get a little bit more shaky. So now we're looking at, what are we looking at here? July, so the kind of the peak melt pond month. We've got the topographic models at the top, the levelized ones in the middle, and that's the melt pond concentration difference versus the observations. And then we've tried to do a similar thing to what we did in our freeboard work, where we tried to look at the plausibility of those differences. So we include observational uncertainty and our estimate of internal variability from some of the models that provide multi ensemble members. And so the hatching is showing regions where we think these are like pretty implausible biases, and we see they're largely concentrated in vast swathes of the Central Arctic, and a little bit more so for those topographic models, but also the CSM2 large ensemble as well for the level ice scheme. The NOR ESM models don't have quite such a strong bias, but they do have stronger regional biases. So if you kind of eyeball these, you see there's some interesting kind of latitudinal or concentration-based dependence of those biases. So that's what we explored next. A little bit hard to see all this. Each panel is a different model. And what we've done here is we've binned the melt pond concentrations based on bins of the sea ice concentration. We did this for the models and the observations. The black line is the same in all of these, and that's the observations. And the point is that the observations show virtually no dependence of melt pond concentration versus ice concentration. Whereas the models seem to show this kind of concentration-based dependence. Seem curious about this. And we especially see that for those NOR ESM models. We see this really, really strong linear dependence of melt pond concentration versus ice concentration. And this is for all the summer months, June, July, and August. So yeah, we're kind of still digging into this and trying to figure out why. And we've been doing a little bit of digging into the schemes. So we're very much still open to discussion on what's driving some of those changes. And maybe some of you have ideas. As I said, the reason why we're doing this work is we're quite interested in seasonal feedbacks. So we've done a little bit of work to see how the models represent seasonal melt for now, both in terms of area on the left column and volume in the right column. And what we're doing here is we're plotting each point is a model's ensemble member for a given year, the seasonal ice loss compared to a melt pond area. And we do that for all the models, and then the black is showing our observational estimates. The bottom row is showing a kind of a normalized anomaly version of those plots. The point is for the observations, we see the positive correlation between melt pond anomalies and seasonal ice loss. But not all the models really produce that. Obviously, when we do this kind of assessment, we need to be aware of the fact observations are only one realization. So we need to try and factor that into these comparisons. So Chris has done some nice work on bootstrapping to try and look at that slope. And we can kind of see whether those models with those limited ensemble sizes produce slopes that are consistent with the observations. And some still seem to do that, but others don't. We're also looking at things like albedo and transmittance. Similar concepts here, where we see a strong relationship between melt pond fraction and sea ice albedo anomalies. We see that in the observations, and we tend to see a much stronger relationship compared to the models. Yeah, so the models are maybe consistently underrepresenting that strength of relationship too. And again, we've done some bootstrapping work to try and understand how consistent that is. So again, the point being that the hope is that if we can improve the melt pond fraction, we can improve some of these relationships and feedbacks. Yeah, we've got kind of a similar plausibility style plots now, but also for melt pond metrics, which we quite like. Again, it depends on the model and it depends on the month, how well they do. Just trying to rush through this. So far, we've all been focused on the Arctic, but our project is very much bipolar. That's what we said we would do. So we have just started to look at what the Antarctic melt ponds look like, which is pretty interesting. You know, most people don't really think or talk about Antarctic melt ponds, but this is a nice Instagram image from Ellen Buckley. And she's cruising through Antarctic sea ice right now, and there's some evidence of melt ponds on sea ice there. And then just our early look at the models is they get even bigger differences across the models of how they simulate melt ponds. So CSM2 produces virtually no melt ponds in the Antarctic, but the UK ESM model, which does a pretty good job in the Arctic, produces very, very high melt pond concentrations, which we find quite interesting. So we've just started digging into this. Hopefully we'll have some more plots that we can show in a summer talk. And I think that's it.
Cool. Thanks. Questions for Alec?
Just something quick. Is this AP? Is this the effective pond fraction you're showing there, or just the actual pond fraction?
I'm not sure. Chris just did this one.
Do it with the effective, not the actual.
Yeah. Well, I don't
No,
know.
we did have a conversation about this recently.
Yeah, I'd like to see the snow with that too, to see it, yeah. It's easy.
Were the temperatures above, at the freezing point when, or melting point when there were ponds?
Yeah, we haven't looked at it, but we will.
It just doesn't get there in CESM, so. That's why it doesn't
Right.
have any meltwater,
Yeah,
so.
Rika.
Well, I think Melinda had a question too, but
Oh, okay.
she was, but then I have something too.
Okay, Melinda, how about you go ahead?
Okay, can you hear me? Did I
Yes.
change the settings? Cool. Really nice presentation, Alec. This is awesome work. And I was struck by the results of the melt pond fractions as a function of the ice concentration. And yeah, that one. And I just feel so skeptical about the black line at the low ice concentrations. Because when ice concentrations are so low along the marginal ice zone, the melt ponds just really aren't there. And I'm wondering if that could be part of the mixed pixel issue that medium resolution satellites have. But, just throwing an idea out there, that's really strange to see that relationship.
Yeah, we've definitely considered dropping that first bin or maybe 2 bins because of those issues you say. Yeah, definitely shouldn't really trust those things too much. I know the MPD2 data set, I think one of the big upgrades from the original was they tried to make a much better effort at kind of characterizing open water as well as melt ponds. But, the sea ice concentration data set obviously has its own problems too. So those long concentrations. So yeah, there's a combination of difficulties in measuring the melt ponds for those low concentrations, then also uncertainty in the actual sea ice concentration data set that we're using to bin it here. So yeah, it's a bit shaky.
Yeah, well, maybe the models are perfect.
Maybe. Still a chance. There's still a chance.
Yeah.
That's very nice coming from you, Melinda.
Melinda, I was just going to say, also with respect to this plot, the runoff fraction in the level ice, level pond scheme is a function of
The ice
concentration.
concentration.
I know. Yeah.
And so there is a reason,
Yeah.
there could be a physical or a
Yeah,
reason within the model why you get this relationship.
Right.
And then I also wonder
But it's confusing.
the
with CSM.
impact
Yeah.
of snow might be, is this,
Right.
is snow fractional coverage or snow thickness
right.
somehow associated with this? It would be nice to look at snow, I think.
Yeah.
Yeah.
We've really done that in this. Yeah.
Yeah.
Especially if you're looking at the effective pond fraction, which I agree with David is what you should be looking at.
So
Because
do you mean in terms of like the meltwater production in it?
well, and you can have meltwater feeding ponds, but they don't show through, which is what the effective pond fraction is.
Right.
Until the snow gets
Right.
thin enough. And so if you have snow sitting around, you can have kind of water pooling underneath, but it's not actually visible.
Right.
And it wouldn't be in your data sets either because it wouldn't be visible. So that's why, so there should be a relationship to snow depth as well.
Right. Yeah, there's a line in Elizabeth's paper about the level ice scheme, which is like, there's this parameter that people should look at some point.
Yeah.
It's ad hoc.
Yeah.
like, how much water do we throw off the ice
Right.
into the ocean?
Right.
Yeah, I would look at whether NORESM
Right, maybe.
uses different RFRAC min and RFRAC max
Yeah, I
in
wonder.
their name
Yeah.
list. That would be the.
All right. Any other further questions? Okay, well.
Very cool.
Say thanks to our speakers. So a few of us are gonna adjourn down in the southern sun. If anyone's interested in going, we have a couple cars in the room, if you ride or whatever, just let one of us know. Otherwise, we get started again at 8:25 in the morning and we're back in this room again, so.
Who is headed to Southern Sun and who needs a ride?
Bye to the folks online.
I have a
Anyone have a
car.
spare